so we're starting with, guys, remember, if you're working on your problem, it's fine. Keep it a little bit lower so that people can hear. All right. We're starting with this one about 2 billion balls that come in at right angles and hit. And then they tell us that ball B goes off along the y-axis. And ball A, they ask us, what's the direction of it? And what speed of ball A after the collision? What's the speed of ball B after the collision? So, all right. So what do we know must be true? Momentum must be conserved. If you didn't start with that in your Y, go back and fix your Y. Must be. In all, I'm going to add in all directions. And then I'm going to do my diagram so that I have before and after. Let's see. Let me just remind myself which way things are going. B was that way, A was that way. Okay. Remember, these are momentum vectors, not velocity vectors. But what relationship does the momentum vector have to the velocity vector? Must be in the same direction. Must be in the same direction. So, and then afterwards, I know that ball B, and I'm going to put a prime on my momentum to indicate that that's after, is in that direction. And then the momentum of A, I don't know what direction it's in. All right. Good. So that's kind of the basic minimum for the Y. Momentum is conserved in all directions, and then showing the before and after momentums. And so, looking at this, the momentum of B that it has afterwards has to be, it doesn't have any of its original momentum left. So all the original momentum that B had has to go into ball A. And all the original momentum that A had needs to go into ball B, the way I'm thinking about it. So I'm going to guess, and this is a guess, so I might put it in my Y. I'm going to guess that ball A goes that way afterwards. And that means I can start with my momentum equation, just so I tick that box off. But the momentum that B has beforehand, I think is going to be the momentum A has afterwards. And the momentum that A had before the collision, that's momentum B is going to have. Remember, them being at right angles to each other means they don't affect each other. So now it's applying my identity. So mass of B, or inertia of B, velocity of B beforehand. Sorry, I forgot my vector symbols on there. Is the inertia of A, the velocity of A afterwards. Anyone want me to go further on this problem, or do you think you can substitute in there? Do you want me to check? I can. Yeah, so this one, this first, this is realistically, this is the x direction and this is the y direction, separating the two. Yeah. Well, let me check my calculations, but it should work. What direction is the velocity of A going to be in? X positive. How would we express that numerically? Zero, right? 0 points x positive, and then we go counterclockwise. So let's see if it is in the zero direction. And it is. So. Yes. Right. You know that my supposition, after I did part A, I assumed, I looked at this and said, okay, well, it makes sense that then A would go directly. And if that's true, then these are true. And I just put in 0 and it's true. Okay. Could also be, it's easy, it would be easy, I think, to swap these. To make that mistake. Right. All of these, that's going to be our basic method. Let's break it into x and y, just to make the math easier. We could do it, with non-right angled trig, line of sines, law of cosines, which might make the math shorter, but it might also confuse people more. But I think we'll break them all into x and y and see where we go from there. All right. So I'm going to move on to the next one if we're good. Okay. Pause this. All right. So two multipliers thrown at each other in such a way that once they hit, they stick together. Ooh, so what type of collision? Inelastic. Excellent. First of all, it's a mass of this, and is moving at a direction of this, as measured counterclockwise from the x-axis. The second ball has a mass of this and is moving with the speed of this in a direction 20.6 degrees, measured clockwise from the x-axis. Once the clay balls join together, they move in the x-positive direction. All right, let's see. Let me, this is clay balls. So, momentum is conserved in all directions, right? And I would probably add in here also, this is an inelastic collision. So I have two objects before the collision. How many do I have after the collision? Just one. Yep. Good. But it has the inertia of both of them combined. So let's see. I have, let's draw these out. The first one, that mass and 23 is measured counterclockwise from the x-axis. So here's my x-axis. Counterclockwise means momentum 1 is going up in that direction. And then my second one is in a direction 20.6 degrees measured clockwise from the x-axis. So that means momentum 2 is in that direction. And then they tell me my final momentum, I'm going to call it momentum total, is in that direction. So 1 and 2 need to combine to be that total momentum. Oh. That means their y parts have to cancel out, right? So if I can only have x left, the two y parts of the momentum have to cancel out. So I'm gonna start off my how with more vector diagrams because I want to get the components here. So I've got momentum 1. It's gonna have components in that direction like that, and then I have momentum 2, and it's gonna have components like that, and the two y parts need to be the same, need to be equal. So let's see, what else? What other information haven't I put in here? First of all, is this mass and is moving in a direction of 22.4 degrees. So for me, that's 22.4 degrees. So this side is P1 opposite, sine 22.4 degrees, and P1 cosine 22.4 degrees. Then, second ball is masses moving at the speed of this in this direction, 20.6 degrees. So this is 20.6 degrees. So this side is P2 cosine, because it's adjacent, 20.6 degrees, and P2 sine 20.6 degrees. We good with what I've done? Okay. So because the final momentum here has to be just in the x direction, I'm gonna do the y direction first. And in the y direction, I have P1 sine of 22.4 degrees plus P2 sine of 20.6 degrees equals 0. I probably should have started off here like P equals mv, right? And then this is my conservation of momentum here. The momentum I have before. Oh, wait a minute, did I put that in right? Shouldn't one of them be negative because they're heading in opposite directions? We want to call down negative? Okay. So I should change this plus to a minus. And now it's right, because I've got P1 sine 22.4 up, and then the part of the P2 down. And let's see, I'm going to just bring that one term over the other side because, I hate negatives because I always mess them up. And substitute in for the momentum. So this would be mass 1, speed 1, sine 22.4. I've already taken care of the direction with my signs above. Equals mass 2, speed 2, sine 20.6 degrees. Oh, what do I know in here? I think I know mass 1. Let's see. Mass 1, yep, 2.23 kilograms. I don't know speed 1. Oh, that's what they're asking me for, though. That's convenient. And then let's see. What else do they want to know? The speed of the combined place after. Okay. So let's do the before and then we'll do the after. So my M1 is 2.23. Now I can substitute in 2.23 kilograms. V1 sine 22.4 degrees equals, let's see if I know M2. I do, 2.95 kilograms and 6.4. So 2.5995 kilograms, 6.40 meters per second, sine 20.6 degrees. And solve for speed 1. See what we get. If you're playing along at home, what you do, double check on your calculator. Degrees, good. I get 7.82 meters per second. I'm going to pause for a second and double check that. All right, so we got the first half. Second half, what is the speed of the combined balls of play after the collision? So now we're going to go into our realm of x, because the momentum afterwards is only in the x direction. So we're going to take the momentum that we have, and you could write it out this way. The momentum of 1 in the x direction plus the momentum of 2 in the x direction equals the momentum total. You're looking for, a way to start that section. And then we can go in and substitute in our individual values, which will look a little nasty, but won't really be that nasty. So we would have M1 V1 cosine 22.4 degrees. We're going to move that. We're going to take as much room as we can. Plus, because they're both heading in the positive direction, if you remember your diagram, M2 V2 cosine 20.6 degrees equals the inertia total, which would be M1 plus M2, and the speed total, which is going to have to be to the right also. No way to have anything to the left, since all of our momentum ahead of time is to the right. And now it's substituting in your values. So for me, that's 2.23 kilograms here for M1. For V1, it's 7.82 meters per second. Cosine 22.4 degrees. Plus my 2.95 kilograms. From my earlier part, right? Just trying to make it hard for you to decide, right? Yeah, I haven't erased any of them yet. And I got 6.52, which seems in the realm of possibilities. Let's check it though. I don't know. Written at the top of your problem set though. Written at the top of your screen, Pat. Yay! All right, let's go for common pool shot. Hitting the ball in the pocket with an angle shown below. Well, it should be a W there. The cue ball hits a stationary ball, sets it, moves at an angle 45 degrees, the original direction of the cue ball, and goes into the corner pocket with the speed of this. Both balls have a mass of this. The cue ball is traveling at this before the collision. This can be considered an elastic collision. So, not only, let's see. So not only is momentum and so is kinetic energy. We have both momentum and kinetic energy conserved. Why do I have this weird little box in the middle? That's because since probably should put since elastic. And then vector diagram, you would have momentum of the cue ball before, momentum of the black ball in that direction, and I'm going to guess that the momentum of the cue ball afterwards is somewhere in that direction. Because since we have only momentum in the x direction beforehand, once they hit, suddenly the black ball has momentum not only in the x direction, but also in the y direction. So to make that y direction bounce out, the cue ball has to go in the opposite direction, has to go downwards. So again, we're going to have our y direction here, momentum-wise, be equal and opposite. So if they add it, because they started at 0 this time, they have to end up at 0, rather than like last time where they started and then needed to end up at 0. So kind of the reverse situation here. I think either place, I'm going to make sure I do the components. So momentum of the black ball. Let's put this afterwards, because really the momentum of the black ball before is 0. And we know this angle is 45. So this would be momentum prime of the black ball, sine 45 degrees, and momentum prime of the black ball, oops, cosine. Cosine 45 degrees. Then you can also do the components of the cue ball afterwards, and they asked me to find what angle is the cue ball deflected from its path by the collision, and what is the speed of the cue ball after the collision. So I'm going to do components in this direction of this vector. This will be theta that I'm looking for, and I'm also looking for the speed of the cue ball. So this will be sine theta, and this side would be P prime C cosine theta. From there, it's really identical to what we just did, right? Our y components are equal and opposite, so they add up to 0. Our x components, we have before equals afterwards. The only maybe a little bit tricky part is that you're going to have a theta in both of them. So mathematically, you're going to come up with two equations with two unknowns that need to solve that way, and then substitute back in. So you're going to end up, with an expression in both that have the unknowns. You guys think you need me to go further, or? Sure, just, you don't want to look just back to your previous one, the one you just finished? Yep. Yeah. Yeah, I mean, you're setting up the y side to be that momentum of the black ball in the y side minus, actually I think, yeah, momentum of the cue ball in the y equals 0, and then you just substitute in, you have those from your components right above, and then in the x direction, you take momentum of the cue ball beforehand equals the momentum of the black ball in the x direction plus the momentum of the cue ball in the x direction. And this you'll end up with not knowing two things, and here not knowing two things, and mathematically bring those together. Okay, so here you'll not know theta. If I look at my parts here, in the y direction I have PB sine theta. I know the mass and I know the velocity of P, right? Of PB. PC, I know the mass, I don't know the speed, and I don't know theta. So, two things I don't know in both of the PC terms. And so, that's going to lead me to mathematically have to solve for the two equations simultaneously. Basically, what I would suggest is solve one of them for V and put it into the other one. And if you need help with that math, let me know. And I'd be glad to come over and look at it individually. But I'd like to go over the firecracker real quick. Yeah, if you need help on the car intersection one, go back and reread that page that you were asked to read, which has the worked out example of the car intersection. All right, so in this one, the firecrackers dropped after falling distance of this, explodes into two pieces of equal mass that are separated by an angle of this. So if they're equal masses, what does that mean about the momentum they take away? They each take away the same amount because they were a whole. They broke into half. You're thinking if we double the mass, then we half the mass, then you're right. The speed would have to double. Here, each mass takes away the same half of it. The other part of this to realize, though, is the firecracker is a projectile or in free fall when it's dropped. And what does it mean to be dropped? Okay, gravity's accelerating it, right? What do you start at if you're dropped? 0. Yeah. So before we can tackle the momentum part, which is the explosion, we have to first say, oh, it falls for this distance. So we have to take into account it's accelerating. What speed does it have at the bottom of it? And then we can go into the momentum part. So it's kind of in that way, it's a two-part problem. So it is in free fall before explodes. Do we call it exploding? Yeah. So accelerating down at little g. And starts from rest. So in my solution part, I'm going to go, okay, it's in free fall. So it's accelerating downwards. I'm assuming you guys can do the vector diagram. Just walking around, it looks like you all had it. You know, it's here, and it has a velocity of 0, and it falls down here the whole time, accelerating at little g. And when it gets down here, for me, 2.04 meters later, it has some other final velocity. And what you want to do is look back on your equation sheet and remember that v final squared equals v initial squared plus 2a delta d. And then once you hit there, now you can go with con of momentum afterwards. All right? And at that point, it's kind of like, oh, the last ones we saw just at an angle, just down rather than to the side. All right, I'm going to save and publish it so I have time to do that. If you need me to look at any individual maps, just call me over, and I'll be glad to look at it with you.